Welcome to day 22 of our system design course. In this session, we will be diving into the high level design process, focusing on mapping business requirements to HLD components and understanding how to approach system design. Let's begin. The high level design process is critical in translating business requirements into a robust system architecture. It focuses on defining high-level components and how they interact within the system. This process is iterative and it seeks to balance both functional and non-functional requirements. System design is not a one-time task. It's a collaborative evolving process. First, let's look at how we map business requirements to HLD components. Business requirements often have two categories: functional and non-functional. Functional requirements focus on what the system should do, like processing payments or managing user accounts. Non-functional requirements, on the other hand, address aspects like performance, security, and scalability. To make these requirements actionable, we break them into high-level components, define system interfaces, and choose the appropriate architecture such as monolithic, microservices, or serverless. When approaching system design, the first step is to fully understand the business requirements, including constraints such as time, budget, and technological limitations. Once we have that, we break down the problem into smaller, manageable components. The key to great design is iteration. Start with a conceptual model and refine it over time. Additionally, selecting the right technologies, databases, frameworks, and cloud services is essential to creating a system that can scale and meet performance goals. Designing for fault tolerance is a crucial part of building resilient systems. We must assume that failures will happen and design accordingly. This includes building redundancy, failover mechanisms, and disaster recovery plans. High availability is key, ensuring that the system remains operational even during failures. Additionally, implementing robust error detection mechanisms like logging and monitoring will help detect and handle failures proactively. There are several important factors to keep in mind during system design. First, security, ensuring the system is secure from attacks and protecting user data with encryption and secure protocols like HTTPS. Second, maintainability, designing the system in a modular way, allowing for easy updates and bug fixes. Third, performance, optimizing for latency and throughput and using caching strategies where necessary. Lastly, scalability, building the system to handle increasing loads over time, but both horizontally and vertically. Let's break down the steps for making business requirements to high level design. First, we need to fully understand the functional requirements. What actions must the system take? Then identify the non functional requirements such as security, performance, and scalability. After that, choose the right architectural pattern, whether it's monolithic, microservices, or serverless. Next, define the system interfaces, how the components will interact with each other and external systems. Don't forget to identify dependencies and constraints to avoid potential roadblocks down the line. System design should always be approached iteratively. Start with a high level conceptual design and refine it over time. Use tools like UML diagrams to visualize how different components interact. Constant feedback and iteration are essential for ensuring the design aligns with the business needs. By regularly reviewing and improving the design, we can ensure the system evolves to meet future requirements and challenges. Proper documentation is a crucial part of any system design process. Documenting the architecture, components, and interaction ensures that everyone is on the same page. High-level design documentation should include architecture diagrams, component definitions, and data flow. Having clear documentation not only helps during the initial development but is also vital for future updates and troubleshooting. In conclusion, the high-level design process provides a clear blueprint for creating scalable and maintainable systems. By iterating on the design and keeping communication open, we can build systems that meet business requirements today and are ready for future growth. Thorough documentation ensures the longevity of the system and helps keep the design adaptable to change. Thank you for joining us today on day 22, and we will continue exploring deeper system design topics in upcoming sessions. Welcome to this presentation on the high-level design review process. Today we will dive into the importance of HLD reviews, the key steps involved, and best practices for conducting effective design reviews. Let's get started. Design reviews play a critical role in ensuring the quality and success of any system. They help in detecting issues early in the design phase, which ultimately saves time and cost. They also provide an excellent opportunity for knowledge sharing among teams, fostering collaboration and improving decision making. Design reviews help align technical decisions with business requirements, ensuring that the system meets both functional and non-functional goals. The HLD review process can be broken down into 5 key steps: preparation, stakeholder involvement, walking through the design, open discussion and feedback gathering, and iteration after review. Let's now take a closer look at each of these steps. Preparation is crucial to a successful HLD review. The first step is to create a clear HLD document that outlines the system architecture, including key components and their interactions. It's also important to define scaling strategies, fault tolerance, and performance considerations. Setting clear objectives for the review ensures that all participants focus on critical aspects such as scalability, fault tolerance, and performance. Next, it's essential to invite the right stakeholders to the review. These include software engineers to discuss technical feasibility, architects to ensure architectural alignment, product managers to verify that business requirements are met, DevOps engineers to evaluate scalability and deployment, and security experts to address risk management. Involving the right people ensures that all critical perspectives are considered. During the review, it's important to walk through the design in detail. Start by explaining the functional components of the system, such as user authentication or data processing. Then demonstrate the data flow between components and how they interact with each other. Finally, discuss the technologies chosen, such as database or message queues, and why they were selected for the system. Open discussion is where valuable feedback is gathered. Key questions to ask include: does the design allow for easy scaling? Are there any performance bottlenecks? Does the design include sufficient failover mechanisms? Are there any security concerns? Encourage participants to express concerns and suggestions, as this feedback is critical for improving the design. Handling disagreements is a common part of the review process. It's important to stay open to suggestions and avoid being defensive. Instead, focus on data-driven discussions and examples to back up design decisions. The goal is to collaborate and improve the design, not to win arguments. A constructive approach would lead to better solutions. Once feedback is collected, it's time to iterate. Prioritize the feedback based on its impact on performance, feasibility, and scalability. Make necessary updates to the design, which could involve adjusting architecture, adding or removing components, or optimizing communication paths. Once the design is updated, revalidate it with stakeholders to ensure that all concerns have been addressed. After the review, it's important to document the outcomes. This includes a summary of all feedback received, the decisions made, and the rationale behind them. Any unresolved issues should be highlighted along with action items for further refinement. This documentation ensures that everyone is on the same page and that any changes are tracked and communicated. Iterative design is a crucial aspect of creating high quality systems. With each round of reviews, the design evolves and improves. Early issue detection is key. Catching problems early allows for timely adjustments, saving resources in the long run. Iterative design also ensures that technical decisions align with business goals, ensuring that the system remains relevant and effective. In conclusion, design reviews are an essential part of building scalable, maintainable, and high performance systems. The review process involves preparation, collaboration, and iteration. By following a structured review process, we can identify issues early, improve the design, and align it with business objectives, ensuring a successful system that meets both technical and user needs. Welcome to today's presentation on designing for scalability. In this session, we will dive into horizontal and vertical scaling, load balancing, auto scaling, caching strategies, and the importance of scalability in modern system design. Scalability refers to a system's ability to grow and manage increasing traffic, data, and users. In this section, we will explore several key concepts: horizontal versus vertical scaling, load balancing, auto scaling, caching, content delivery networks, and sharding. These strategies ensure our system can efficiently handle large scale growth. When we talk about scaling systems, there are two approaches: vertical scaling and horizontal scaling. Vertical scaling, also known as scaling up, involves adding more resources like CPU or RAM to a single machine. While it's simple, it's limited by hardware capacity. On the other hand, horizontal scaling or scaling out adds more servers to distribute the load. This approach is more flexible and cost effective but can be complex to manage. Load balancing ensures that incoming traffic is distributed across multiple servers. There are various load balancing strategies: round robin, least connections, and weighted round robin, each offering different benefits. Load balancing enhances the availability and reliability of our system by preventing any single server from being overwhelmed with too much traffic. Autoscaling is a process that automatically adjusts the number of active servers in response to traffic. For instance, if CPU usage exceeds a certain threshold, additional servers are added. This automatic scaling helps maintain optimal performance while being cost effective by scaling down during off-peak hours. Caching plays a crucial role in scalability by reducing database load and speeding up response times. In memory caching like Redis or Memcached stores data closer to the application. Distributed caching spreads the data across multiple servers to enhance reliability. Managing cache expiration and invalidation ensures that our system always serves up-to-date data without unnecessary load. Content delivery networks or CDNs are a network of distributed servers that deliver content to users based on their geographic location. By offloading traffic from the origin server, CDNs provide fast content delivery, improved availability, and redundancy. This is essential for applications with global user bases as it helps minimize latency. Sharding and partitioning are techniques used to divide large datasets into smaller, more manageable pieces. Sharding spreads data across multiple servers, often based on specific criteria like user ID or region. This helps improve performance and scalability, especially when dealing with large volumes of data. Implementing these scalability strategies requires careful planning. For example, in database sharding, we can partition data by user ID or region to reduce bottlenecks. Cloud services such as AWS or Azure provide elastic infrastructure, allowing for flexible scaling based on demand, ensuring our system can grow seamlessly. Designing for scalability often involves trade offs. One common challenge is the Cape theorem, which outlines the trade offs between consistency, availability, and partition tolerance. When scaling horizontally, we may need to decide between ensuring data consistency or maximizing system availability. Additionally, handling data duplication and maintaining consistency across distributed data is another important challenge. Several tools and technologies can help us implement scalability. Autoscaling tools such as AWS Autoscaling or Google Cloud Autoscaler adjust resources dynamically. For load balancing, tools like Nignix or HAProxy help distribute traffic effectively. CDNs like Cloudflare or AWS CloudFront ensure faster content delivery, and caching systems like Redis and Memcached reduce server load. In conclusion, designing scalable systems is essential for handling increased traffic and data. Horizontal scaling, load balancing, auto scaling, caching strategies, and CDNs all play crucial roles in ensuring that our systems can grow efficiently without compromising performance. By leveraging these strategies, we can build resilient systems capable of handling future demands. Welcome to the presentation on designing for fault tolerance. Today we will explore how to ensure system resilience and availability in the face of failures. Let's begin by understanding what fault tolerance is. Fault tolerance is the ability of a system to continue functioning even when one or more of its components fail. It is crucial for ensuring high availability and minimizing service disruptions, making it a key principle in reliable system design. Fault tolerance relies on three key components: redundancy, failover mechanisms, and disaster recovery. Let's take a closer look at each of these. Redundancy is about duplicating critical components in a system to avoid single points of failure. There are different types of redundancy. Hardware redundancy involves having backup physical components like servers or storage. Software redundancy involves running multiple instances of software to ensure uninterrupted services. Data redundancy stores copies of data in multiple locations, safeguarding against data loss. An example of redundancy is RAID, or redundant array of independent disks. RAID combines multiple disk drives into a single unit and ensures data protection in case of drive failure by using various redundancy levels. Failover mechanisms automatically switch to backup systems in case of failure. There are two main types of failover: active, passive. One system is active and the other is on standby. Active. Both systems are active and they share the load, ensuring no downtime. Consider a database system with failover. The primary server handles all requests while the passive replica remains idle. In case the primary server fails, the replica automatically takes over to maintain service continuity. Disaster recovery involves strategies for recovering from catastrophic failures. Key elements include a backup strategy that stores backups in diverse locations, RPO or recovery point objective, which defines the maximum acceptable data loss, RTO or recovery time objective, which specifies how long the system can be down before recovery becomes unacceptable. Disaster Recovery as a Service (DRaaS) provide cloud-based services to ensure fast recovery of services and data. With DRaaS, businesses can quickly restore critical systems and minimize downtime following a disaster. Regular testing of disaster recovery plans is essential to ensure that the system can be restored efficiently. Testing can involve tabletop exercises which simulate scenarios to practice response strategies, simulation drills which test recovery procedures in real time, full-scale recovery testing which validates the complete recovery process. In fault-tolerant system design, several design patterns are essential for maintaining system stability. The circuit breaker pattern prevents cascading failures by halting requests to failing services. The bulkhead pattern isolates components to prevent failures from spreading. The retry pattern attempts failed requests again. The fallback pattern provides an alternative response if a service fails. Continuous monitoring and logging are critical for early fault detection. Tools like Prometheus, Grafana, and the ELK stack help monitor the health of the system and trigger failover mechanisms when necessary. Monitoring ensures that the operations team is alerted to issues before they escalate. In conclusion, fault tolerance is a key aspect of modern system design. By incorporating redundancy, failover mechanisms, and disaster recovery, systems can continue functioning even in the event of failures. Regular testing and monitoring ensure that systems remain resilient and operational at all times. Thank you for your attention. If you have any questions, please feel free to ask. I would be happy to clarify any doubts. Welcome to day 26 of the System Design Process and Best Practices course. In today's session, we will be focusing on designing for performance. We will cover key aspects such as latency, throughput, response time, caching strategies, and content delivery networks (CDNs). In this session, we will discuss the core concepts of performance design. These include latency, throughput, response time, caching strategies, and the role of content delivery networks or CDNs in improving system performance. Let's begin with three essential metrics: latency, throughput, and response time. Latency refers to the time it takes for data to travel between the client and server. Throughput measures the number of requests processed per second. Response time is the total time from when a request is initiated to when the response is received. To reduce latency, there are several strategies we can adopt. Firstly, we can use content delivery networks (CDNs) to cache data closer to the user's location. Minimizing database queries and reducing the number of hops between services are also key strategies. Additionally, optimizing code and identifying slow operations can significantly reduce latency. Throughput can be improved by employing techniques like load balancing, which distributes traffic across multiple servers to avoid overwhelming any single one. Parallel processing allows us to handle multiple requests simultaneously. Lastly, using queuing systems like RabbitMQ and Kafka for asynchronous processing helps in better handling of large volumes of traffic. To reduce response time, database optimizations like indexing and query optimization are crucial. Server-side caching helps avoid redundant computations, and asynchronous processing can minimize blocking operations. These techniques help make the system faster and more efficient. Caching is a powerful technique to improve performance. We can implement client-side caching where data is stored locally, server-side caching where data is cached at the server, and distributed caching where tools like Redis or Memcached. It also important to choose a cache eviction strategy such as recent least recently used LRU, first in first out FIFO, or least frequently used LFU. Cache invalidation is another key concept. We need to ensure that cache data remains up to date. This can be achieved through mechanisms like time to live (TTL), write through, and write back strategies. These techniques help us manage data freshness and optimize cache efficiency. Content delivery networks or CDNs are networks of servers distributed across multiple locations. They cache content closer to the user's geographical location, significantly improving access speed. CDNs help in reducing the load on the origin server and provide a more reliable content delivery experience. CDNs improve performance by reducing latency, serving content from servers located near the user's location. They also enable better load balancing by distributing traffic across multiple servers and provide faster access to static content like images, videos, and documents. Performance testing and monitoring are critical to ensure the system meets performance goals. Load testing simulates high traffic to test how the system handles the load, while stress testing evaluates its breaking point. Tools like New Relic, Prometheus, and Grafana can help monitor system performance in real time and provide insights for improvement. There are several performance metrics we need to track, including response time, which measures how quickly requests are processed, Throughput indicates the number of requests handled per second, while error rate shows the percentage of requests that result in errors. Monitoring resource utilization such as CPU, memory, and bandwidth usage is also important to maintain system efficiency. In conclusion, to design for performance, we must focus on reducing latency, improving throughput, and optimizing response times. Implementing effective caching strategies and leveraging content delivery networks are essential for boosting system performance. Continuous monitoring and testing will ensure that the system remains optimized and scalable. Thank you for your attention. If you have any questions or need further clarification on any topic, feel free to ask. Welcome to today's presentation on designing for maintainability. In this session, we will cover the key principles and best practices to ensure that our system remains sustainable, easy to maintain, and evolves efficiently over time. Here's a quick overview of what we will be discussing today. First, we will explore code modularity and why breaking down our system into independent components is so important. Then we will dive into separation of concerns, helping us to better organize our system's functionality. Next, we will talk about testability, ensuring our code is easy to test and maintain. We will also discuss code review and pair programming, collaborative techniques for improving code quality. Then we will cover documentation standards to ensure our system is well documented for ease of understanding. We will touch on version control as a means to track and manage code evolution. After that, we will look at refactoring, a technique for improving code quality without changing its functionality. Finally, we will wrap up with monitoring and logging, essential tools for tracking system performance and issues. Let's start with code modularity. Modularity involves breaking down our system into self-contained, independent components. This is essential for maintaining a clean architecture and making our system more manageable. The key principles of modularity include the single responsibility principle, ensuring each component has one job, and cohesion, which ensures that related components are grouped together. On the other hand, loose coupling minimizes dependencies between modules, making them easier to modify independently. The benefits of modularity are clear. It makes our code easier to debug, test, and scale, while also supporting parallel development efforts. Next, let's talk about separation of concerns. This principle means organizing our system so that different concerns like user interface, business logic, and data storage are kept separate. One common approach is to use a layered architecture where each layer handles a distinct responsibility. This improves clarity, reduces interdependencies, and makes it easier to troubleshoot and extend the system. Separating concerns also allows each layer to evolve independently, which is crucial as our system grows. Now let's discuss testability. A maintainable system must be easy to test. By ensuring our code is testable, we can catch bugs early and verify new changes without fear of breaking existing functionalities. Some key features include dependency injection, which makes it easier to inject mock dependencies for testing, and test-driven development (TDD), where we write tests before writing the actual code. Mocking and stubbing are other strategies used to simulate real-world conditions in unit tests. A testable system is easier to maintain because we can identify and fix defects quickly, ultimately improving the stability of our code base. Next, let's discuss code review and pair computing. Code reviews are a collaborative process where developers review each other's code to catch issues early and ensure quality. Regular reviews not only help improve the code but also spread knowledge across the team. Pair programming is another collaborative technique where two developers work together on the same code, providing real-time feedback. This improves problem solving and accelerates learning. Both of these techniques contribute to higher code quality and foster team collaboration. Moving on to documentation standards, proper documentation is key to ensuring that our code can be easily understood by other developers or even our future self. There are three main types of documentation: technical documentation, such as architectural diagrams or API specs; code comments, which explain complex logic; and user documentation, which guides end users or administrators. Best practices include keeping documentation up to date and using clear, concise language that anyone can understand. Now, let's talk about version control. Version control systems like Git track changes to our code base, allowing us to manage and revert changes as needed. Best practices for version control include writing clear commit messages, making small incremental changes, and using feature branches to develop isolated features. Version control not only helps in tracking changes but also enables collaboration, ensuring multiple developers can work on the same code without overwriting each other's work. Next up is refactoring. Refactoring is the process of restructuring our code to improve readability and maintainability without changing its behavior. Common techniques include extract method, which simplifies large functions, and renaming variables to use meaningful names. Removing duplicate code is another important technique to consolidate similar logic into a single function. Refactoring reduces technical debt and makes our code base easier to modify as new features are added. Lastly, let's discuss monitoring and logging. These practices are crucial for detecting and resolving issues in real time. Monitoring tools like Prometheus or Grafana track system health and performance, while logging systems like ELK Stack or Splunk capture detailed information about our application's behavior. Using structured logging helps us easily parse and analyze logs. These tools allow us to proactively address issues, minimize downtime, and ensure our system runs smoothly. In summary, maintainability is all about designing systems that are easy to manage, evolve, and troubleshoot. By focusing on modularity, separation of concern, and testability, and leveraging practices like code reviews, pair programming, and refactoring, we can create a more maintainable system. Additionally, version control, documentation, and monitoring provide support for long-term system evaluation and reliability. Thank you for your attention. I hope this presentation has provided you with valuable insights into designing for maintainability. If you have any questions, please feel free to ask. Hello and welcome. In this presentation, we will analyze the high-level design (HLD) of a popular e-commerce website. We will dive into the system architecture, design decisions, and components that ensure the scalability, performance, and reliability of such systems. In this case study, we will focus on analyzing the architecture of a widely used e-commerce website such as Amazon or Flipkart. Our goal is to understand the different components that make up the system and how they work together to deliver a seamless online shopping experience. Let's start by looking at the business and functional requirements. The system must handle millions of users, transactions, and products in real time. Key user requirements include high availability, fast response times, and a smooth checkout process. On the business side, the website must support a variety of products, secure payment transactions, and integrate with third-party services like shipping and inventory. Now, let's break down the system components. The e-commerce platform consists of several key components, including the front end for user interaction, back-end services for processing, database for product and user data storage, and various integrations like inventory management, payment gateways, and shipping systems. Together, these components form the backbone of the website. Key design decisions play a significant role in how the system performs. Scalability is one of the primary concerns, so horizontal scaling and load balancing and auto scaling are used to handle increasing traffic. Fault tolerance is crucial to ensure uptime, which is achieved through redundancy and failover mechanisms. For performance, caching strategies and CDNs are employed to ensure fast access to data. Maintainability is supported by modular design, CI/CD pipelines, and comprehensive monitoring. Scalability ensures that the system can handle an increasing number of users and transactions. Horizontal scaling, which involves adding more servers, is a key technique used. Load balancing distributes incoming requests to multiple servers, ensuring no single server is overwhelmed. Autoscaling dynamically adjusts resources based on demand to maintain performance even during traffic spikes. To ensure the system remains available even in the event of failure, fault tolerance is built in through redundancy. This means that critical components like web servers and databases are replicated across different locations. Failover mechanisms ensure that if one server fails, another takes over. Additionally, disaster recovery plans ensure quick data restoration if needed. Performance is a critical aspect of e-commerce platforms. Caching systems like Redis and Memcached are used to store frequently accessed data, reducing database load. Content delivery networks (CDNs) help in delivering static assets such as images and videos from edge servers located closer to the user, reducing latency. Additionally, low latency in the application ensures faster response times for the users. Maintaining a large-scale system requires robust practices. A modular microservices architecture is used to ensure easy updates and independent scaling of services. Continuous integration and continuous deployment (CI/CD) pipelines automate testing and deployment, speeding up development cycles. Monitoring and logging systems track performance, errors, and health system, allowing quick issue detection and resolution. Security is paramount, especially when dealing with sensitive user information. Payment transactions are encrypted using SSL or TLS. For user authentication, secure protocols like OAuth and JWT tokens are used. Furthermore, protections against DDoS attacks, SQL injections, and other vulnerabilities ensure that the system is resilient to malicious activity. When designing large-scale systems, challenges like handling traffic spikes, ensuring data consistency, and managing seasons can arise. To tackle this, horizontal scaling and load balancing help with traffic management. Distributed transactions and event sourcing handle data consistency. For session management, JWT tokens and centralized session storage are used. To summarize, the design of an e-commerce platform involves a careful balance of scalability, fault tolerance, performance optimization, and security. High-level design decisions like modular architecture, redundancy, and caching help the system achieve reliability and efficiency. By focusing on maintainability and continuous improvement, these systems can scale as needed to support millions of users. Thank you for your attention. Now I would like to open the floor for any questions. Feel free to ask about any aspect of the system design, architecture, or the challenges discussed in this case study.